waiting for other people to join. Yeah, just waiting for other people to join. Let them trickle in. Some familiar names already. Hey, hi, Girisha.
Hi. Yeah,
Um,
it's my first
like,
time today.
yeah, welcome to the research jam. Where are you joining from?
Thank you so much. I'm joining from New Delhi.
Sounds good, Nisha.
Yeah,
Welcome.
lost my
Thank you.
internet for a bit. Girisha, could you uh, repeat where you're joining from?
Yeah, sure. So I'm joining from New Delhi.
Nice, nice. So you're working somewhere? Would love to know more
Mm.
about what you're doing.
Yeah, so I'm currently in my final year of engineering at IGDTUW, Indira Gandhi Delhi
Great,
Technical
great. Where?
University for Women. Indira Gandhi Delhi Technical
Oh,
University for
nice.
Women. I'm very interested in this AI, ML, and LLM space. And I've recently started exploring
Very
LLM,
nice.
so I'm quite excited for this discussion. And also, I'm an incoming master's in AI student at Imperial College London. So, yeah, that's about me.
Very nice.
Thank
No,
you.
congratulations on your admit to video.
Thank you so much.
Yeah, and having a good session. We'll get started as more people come in. Hey, hi, Thea.
Hello.
Uh, Welcome to Genloop Research Jam. Love to know more about you. Where are you calling from? What are you doing right now?
Hello. So I'm a first year student at IGUTW. I'm currently doing my BTech in information technology, and this is my first session here. Actually, this was
Nice.
recommended to me by one of the attendees here, Pooja Gera. She posted it in her
Oh,
WhatsApp group,
nice.
and that's how I got to know about this session.
Very nice. Welcome. Let's wait for another minute. Ayush, maybe we can start sharing the screen.
Okay. Is it visible now? Screen.
Yeah, visible. Perfect. Yeah, so let's start. Welcome everyone to Genloop Research Jam 3. Here we'll be covering small VLM. So it's a series of models released by Hugging Face on how to build small sized vision language models and the technical report associated with it. So we'll be covering it. We'll be trying to learn from the experiments that they conducted and see, discuss about that in a free conversation. Next slide, please. So a very quick TLDR about Genloop. We are in the space of building domain intelligence seamlessly for enterprises. So we help enterprises embed their business know-hows and knowledges onto LLMs and use them in their production workflows and use cases without the added effort that customization normally brings. So we have AI agents that automate the entire dev effort in three simple steps, which is ingesting the data, preparing it, training multiple models autonomously and finding out the best fit, and deploying them with a single click and improving them with continuous learning. Next slide, please. So the paper. So the paper we're covering is taken from LLM Research Hub. This is our portal where we source the best papers across and rank them in terms of popularity, quality, and impact. And for the last week, small VLM was the most impactful paper, so that is what we are picking. Next slide. So that's our space to discuss Gen AI research periodically. So we do bi-weekly sessions, and again, welcome to everyone, and let's just dive deep into this paper, small VLM. Over to you, Anush.
Okay. So before diving into the paper, let's go through a bit of preliminary on how VLMs actually work. So suppose you have an image of a say elephant, and you ask a question to a visual language model as in what's in the image. Okay. So what a VLM does is that it takes both the image and the text as input and maps the image which you are giving to a corresponding textual description. To put it simply, for example, you have an image of elephant. So the first step the VLM would try to do is map this image of elephant to an equivalent textual embedding, because the main backbone of VLMs is a large language model, and it does all the processing for the VLM. So what we require is a representation of an image that could be represented in the textual domain. So this is a very key feature of VLMs, in which an image is transformed into its corresponding textual embeddings. Okay. So the key highlight of this paper was small and compact VLMs. So previously there have been various efforts in which larger VLMs were transformed into smaller VLMs, reducing the number of parameters and keeping the overall method same for tokenization, for encoding. But the problem with this approach is that the things which work on larger VLMs might not work on compact and small VLMs. So what the small VLM paper does is that it tries out different methods at different stages of a VLM training and finds the most optimal method that would work for a compact visual language model. Okay, so any doubts up till here about how VLMs work and how the overall things work? Then we can dive into the paper. Okay. So let's move on. So let's move on with the architecture of the small VLM paper. So suppose we have an input image. So the first step is image splitting. So what image splitting does is that it breaks the image into grids and then passes these grids to a vision encoder. This vision encoder, what it does is that it transforms these images into a low representation feature space. Then there is another method called pixel shuffle. What this pixel shuffle does is that it reduces the number of tokens that were there after the visual encoding, and then there is a linear layer which maps these final encoded images to a representation that is understandable by LLMs. So this was the overall architecture, and we'll move on in detail in the next sections.
And just one quick pointer on pixel shuffle.
Hmm.
It's a very interesting approach on how they are compressing the token length. So basically, let's say we have an image of 32 by 32 into 3. Like images are even you know um, more in this length and breadth than this, but just for discussion sake, what they're trying to do is they increase the channels and compress the length and breadth. So basically from, let's say, 64 by 64 by 1, they would make a 32 by 32 by 3 kind of a denser representation and compress it further to a 16 by 16 into 10 kind of a representation, and increase the channel depth and condense the same information there. So pixelate the information on the length and breadth size, but increase the same density of information on the channel. So then the token gets denser and you require less tokens when you are splitting the image into multiple patches.
So here every channel is corresponding some feature, right? Certain kind of feature of the image.
Yeah. Basically, so the way the tokens are created are by slicing the image, including across the channels, into multiple patches. So that patch could get denser with channels, but since the size of the image is small, you require less number of patches.
Okay.
Okay. So the key takeaways which can be inferred for this is that they contributed 3 open source VLMs, and the smallest size VLM could even run on a 1 GB GPU with batch size of 1. They even beat a 80 billion parameter model, which is 300 times parameter of this, and achieved very comparable results. And one of the main highlight was that making small integrate changes at different architectural levels lead to a bigger change in performance at the end. We would look at all of these changes in the next slides. So the first is the choice of encoder. So the first step in a VLM is encoding these images into a latent representation. So what they found is that a balance between the encoder and decoder means there is a vision encoder and there is a language model. The sum of these will contribute to the total number of parameters in the model. So a balance between the size of the vision encoder and the size of an LLM is preferred for compact models. So what they did is that they tested with two vision encoders, one of 93 million and one of 428 million, and they tried to do that with different sizes of the LLM part. So what they notice is that as you can see in the graph, this blue and orange graph at the bottom, you can see that the first dot is a 135 million language model combined with a 93 million parameter encoder, and this is the same sized LLM combined on the 428 image encoder. So what they found is that a 93 billion parameter model combined with a smaller language model yields better performance than combined with a more larger vision encoder and a smaller LLM. This is because of the fact that smaller language models could not capture more information from the image as compared to a smaller language model. Okay, so that's so the main conclusion is that for compact VLMs, a more balanced encoder-decoder architecture is benefited. So, for example, if we have a 93 million parameter vision encoder, then a 135 million LLM would be beneficial as compared to a 428 million parameter vision encoder. Okay. Okay, fine. Let's move on. So the next is the increasing the context length and tokenization. So let's focus on the LLM. So the LLM they utilized was the SmolVLM2. So the SmolVLM2 has a very small context length of around 2K tokens. So and if you include the image tokens in it, the image tokens of a good sized image around 512 cross 512 would take up around 1024 tokens. And therefore, due to this, a large amount of tokens would be included in the vision part only. So there would not be enough space left for the text part. So the first change that they did to it was to increase the context length of the existence language model by increasing the base of the row positional encoding. So if we get into detail of what rope does is that you might be familiar with the sinusoidal positional embedding in which were proposed in the initial transformer paper. So what a rope does is that it maps the position based on a rotation in the complex plane. So for example, if you have a lower base, then you would be able to encode lesser information, lesser number of tokens, and if you have a higher base, say 10,000 and 20,000, then you would be able to encode a text of more context length. So what the first thing that they did was to increase the context length. So for increasing the context length, they increased the base of the row positional embeddings. So, but only increasing the context length could not increase the understanding of the VLM on the increased context length. So another thing they did was to compress the visual tokens. So to compress the visual tokens, what they did is that they included pixel shuffle, as Ayush described earlier. What
Just one more point there, Ayush. Sorry for interrupting. So, of course, with small VLMs, the objective is to have a smaller form factor model be able to be uh, ready for edge deployment, etc. So again, like you've said the context already, that the entire architectural choice, etc., was that you cannot just scale down the architectural choices for a larger VLM to a small VLM. Like small VLM requires their own experimentations or their own architectural choices that can suit their need. And one beautiful thing about this paper is that many of the recommendations and experiment observations that they've conducted are pretty much intuitive. Now, on context length and tokenization, I remember they mentioning that they could go up to 8K tokens for the smaller VLMs. So basically less than 1 billion VLMs. And after that, they did not get enough performance gains. They could go with a higher context length for the 1.7 billion VLM. So I remember something around that. And that also made intuitive sense for me. Like there is, even with rope scaling, there might be a limit to how much context length you want to increase with a smaller VLM. And before you start on that pixel shuffle, and that also makes sense. Like, images are taking 1024 tokens. Like if I build a VLM with a 2048 tokens, I don't have enough space left for text embeddings. And to be able to work with a smaller VLM, I need to do both. I need to have compressed text embeddings and compressed vision embeddings, and try to fit the best number of context length that I can do. So that is where they tried, even the vision one, let's try to embed more vision information in a smaller context length so that we can express the text part of it without limitation. Yeah. So that was just one observation I wanted to add.
So next is the efficient encoding. So as you can look at the architecture, so then the next thing is how we can efficiently encode the image into the visual encoder. So the next thing they adopted was image splitting. So whatever happens if we have a larger image, say 512 cross 512, it would be difficult for a smaller VLM to comprehend this entire image. So a thing that they adopt is splitting these images into small patches and then giving once the entire image and then the individual patches as input to a vision encoder and correspondingly to a language model. And then each of these patches, as you can see where I'm pointing, so this 1 cross 1 is the entire image, 1 cross 2 is the first one, then this, then this, then this. So what it does is that it gives individual patches of the image also as input to a VLM. Okay. So this is one thing that they adopted. Another thing with videos specifically was that enhances performance on vision, whereas so image splitting does work, but the video frame averaging does not work with their experiment. So that's all with this.
And they don't provide any, any supporting intuition for this, like why video frame averaging does not work, or if they provided, I was not very convinced with it. But this is something empirical that they observed in this case.
Experimental. I also saw it.
Yeah.
Yes. So this was till the architectural changes that they did. So next are the changes that they did in the instruction tuning of these VLMs later on. So so what happens is that suppose we have splitted the images into different patches, and now we have to give these individual patches to so suppose at the end we have also encoded these images, have embeddings for all these patches. Now how we will pass these embeddings to the LLM? So the first approach they adapted was simply using a string. We will label all the patches that this is the embedding of row 1 column 1 image, this is the embedding of row 2 column 2 image. But what they noticed was that there was during training the loss was going down and down and down and down, and there was sudden decrease in loss. But the problem with that this decrease in loss was not corresponding to an increase in performance. So what they did something to it, that they replaced these string based position for the image embeddings with a learned embedding for all these image patches. So as you can see, these learned embedding perform better than the previous string embeddings, and there was not this reduction in loss, as you can see here.
Right. And I think they also mentioned that there was some kind of a loss hacking happening there when they were giving string-based tokens.
Yes.
And the model essentially wasn't able to learn anything, any proper thing when doing these string-based tokens for embeddings.
That's what they mentioned in OCR loss plague.
Yeah.
So the problem. So the one thing with small VLMs is that the language part is not pretty strong to understand all the textual description that we give. So they resorted to fixed structured prompts that would be given to a model for each task. So they adopted structured system prompts, structured labeling as to which part of the video they are referring to, which part of the image they are referring to, and they found that this worked pretty well. And another thing was that the text data proportion in training. So a normal practice with training larger VLMs is that they also include a large amount of textual data, not only multimodal data, but also textual data in the training part. But what they noticed with smaller VLMs is that increasing the proportion of this textual data led to a very drastic decrease in performance, because what they were essentially doing is overfitting this on textual data, which was not beneficial for smaller VLMs.
Actually, one more thing was for from the structured text prompt perspective, and this is again very intuitive as well. The intros, outros were very important to delimit the media content. That okay, saying that okay, this is now the image, and then sharing the image part of it, or that was something that gave them a very good improvement in performance. Otherwise, we know that without system prompt and with system prompt, there's definitely some kind of an improvement. Um, and on text data proportion, uh, that was also, I think they also mentioned something, right? Like why adding text data during SFT is not giving them VLMs, like benefit in VLMs.
Yeah, what I saw that it was overfitting on the textual data and forgetting its visual capabilities.
Right. And that is the problem with the smaller size models. So in all the experiments that we have also done, like playing with the smaller size models, we see that they definitely lack reasoning capabilities, or like they lack instruction following capabilities. So like we all know that so far the LLM's reasoning capabilities are directly proportional to the data size, and it's more like a cliff, or like a step function. Like up to 1 billion, the models are less capable of reasoning. Then from 1 to 5, they are similar. Then 5 to 15, they are similar. Then 15 to 30. Basically, that is the kind of step function. So less than 1 billion, the models are very less capable of reasoning. So any kind of this textual mix or these confusions of more text definitely overwhelms the VLM or the LLM and makes them forget learning well.
Yes.
Any questions, anyone so far? I'm sure like someone would be having um, an interesting point here to discuss.
I have one question.
Mhm.
Like during training, they said that they have created patches of the image and pass it to the model. So why not wasting the context length there? Use it in text and pointing out that I have the problem in let's say I have passed one image and I am passing a text like something in the right corner of the image. I have to do certain analysis or what. So why not increase the text context and decreasing the image context?
Why not increasing the text context and decreasing the image context?
Like reducing the patches, like not introducing patches, like directly giving the full image instead of passing patches.
Giving the full image
Yeah, and
rather than
pointing out via text that I want some analysis on the right corner of the image or some kind of this. So maybe.
But I think that's the problem with the small encoders. So, for example, if you pass an entire image, it would pretty much lose the
Right.
spatial information of the image. But instead of it, if you would pass the individual patches, it would better encrypt all the spatial information that is within that small patch. Basically, you have zoomed in that part of the image and then asked the encoder to encode that part. And to an LLM, you are giving the information that in this patch, this information is there. Then towards the right of this patch, this information is there. Towards the bottom of this patch, so it gains all the spatial information as well, and you also have the compact zoomed in information for each of those pixel. I think that's the reason they do that.
Okay. Right. And like one of the top papers this week is the intern VN3. And it follows like while we are on the subject of incorporating image information into a VLM, it follows a different approach of VLM training. So like until now, it's like, let's give some image information, encode it, and, um, put it in the LLM as an adapter and then cross attend or like add a cross attention with the textual part of it so that the core LLM starts making sense of it. So there's no native image training that happens with it. The intern VL3 is proposing a paradigm where we can directly, pre-train on images as well. So the point being that, there's continuous innovation happening on the training side of things as well.
Yeah, yeah.
Right.
Like kind of text is given more weightage over image.
Yeah, yeah. Like VLMs on the core are VLMs or any multimodal LMs in production today are more LLMs that are fed informations of other modalities through some kind of an adapter.
Okay.
Yeah, but great question. A third.
Okay, so should we move on?
Yeah, please.
But one interesting thing that they see was key. So the previously we have seen that increasing the test proportion led to a decrease in performance, but increasing the COT data for a very small proportion does increase the performance, but it too leads to a decrease in performance as you increase the increase the proportion. I saw in the paper it was around 0.05% of the entire data, but it's pretty
Uh,
low.
and this is also intuitive. Like it's akin to saying that you are making a very low IQ model having to do a lot of high IQ tasks.
Hmm.
So it starts performing badly even on the tasks that it could have performed well on.
Yes.
So basically pushing the model in depression kind of a thing.
Mhm. So another thing that they've seen was increasing the video sequence length for the VLM task improves the performance both for the image as well as video task in case of compact VLMs, as you can see in the graph below.
Right.
I was not able to get the intuition around why this was happening. If you could think it.
And any takers? Anyone wants to propose any hypothesis why increasing the video duration improves the model's performance on image tasks? An image task has something like captioning the image, etc.
So I think if we think about like the bare like the brutest answer to this, it could be that more data frames, more data point is equal to the model actually trying to understand the context as well as what we're trying to achieve here. So it just gives more data points there.
Right. No, I agree. It could be that, but it could also be argued like they could have shared the number of video examples. So basically, if the thing is that a increase in the video duration means more training examples, a similar performance lift should have been achieved uh, if the samples of images is increased, or if they trained on more image data. They would have seen a similar performance improvement. So
I think I can have a go at it. So
Yeah.
what I feel is, so right now you have a video, right? In an image, everything is still. There is less correlation, but in a video, you have moving characters, you have like dimensionality, like a much higher dimensionality. There's so at that stage you have more information about reasoning or maybe like how exactly these objects work. So at that
Mm.
stage, maybe that might be something that is getting compressed into these models.
Mm. I think I borrow from that idea. Like when we have increased the video duration, we are possibly making the model learn better about correlations between different frames, or basically the temporal understanding of movements in videos, etc. Does that help the model improve its learned positional embeddings in any way? Like maybe that is helping. I don't know, but that is something for us to explore. Yeah, are you using something?
Maybe, yeah. I found that reason good. Right.
Yeah, like Pooja and Vansh both gave good reasons. Like, definitely with higher video duration, we have more examples. Then with increasing video duration, we are making the model understand more about the spatial information about images, or the temporal understanding of images, how one image is leading to the another, and what are the spatial elements of it, etc. Maybe and how that impacts the model, because just increasing the video samples or increasing the image samples is not giving that spatial information or the temporal information so much. So maybe that helps the model understand, what part of the image is doing what, or how are things moving between images, and that is improving its spatial understanding of the image.
Yes.
Yeah. Makes
So
sense.
next we'll move to the last section, experiments and result. So what they did is that the first stage is a visual training data. So the most of it part was the image and some part was text. In text, they basically included reasoning and logic and general knowledge question, which was part of the training of the LLM only. And in images case, they took different subdomain images, and next was the visual fine-tuning stage in which they so one interesting thing was that they didn't train it on videos in the visual training stage only. They trained on video only during the fine-tuning stage. So they combined with a small proportion of multi images input as well, in which you have multiple images and a question that is asked on these multiple images, 2 to 3 images, and on single images, on videos, on text, uh, and that's how they achieve.
Mm.
I don't think so. There's nothing more in it. Yes. Hmm. So these are the results from all the 3 sizes that they released. So as you can see that even the smallest small VLM 256 million performed comparable to a 7 billion parameter model, which was quite surprising. Because what essentially did is that they borrowed different ideas from all the previous researchers and combined it to one. That was pretty interesting. Anything more to add in the results?
I think it's highly correlated to the data as well. One thing I was observing from the training data distribution was that um, diagrams, like if you go to the previous slide, this chart understanding was just 12%, so even less than the text or something, right? And if you go to the right again, the next slide, so AI 2D, science diagrams,
Hmm.
that is kind of very poor compared to the 7 billion model.
Hmm.
OCR was 48%, and that is where you are seeing that 52% of the 256M performance.
Hmm.
Chart QA is doing decent though.
Maybe
Text,
OCR is a easy task for it to do.
and the data is also high. So
Ah,
maybe it's easy. Plus, it has been fed enough examples for that.
yes.
Doc VQA, even visual question answering examples. See the VQA. So I think if you go back, the visual question answering was just 8%.
Hmm.
And then here, the performance is quite dismal.
Hmm.
So definitely there's correlation between the size, or basically the percentage of the task in the training data and the performance.
Hmm. Pretty
If
much.
we go near, see general video understanding is so poor. Like, of course, like there's less reasoning capabilities in a 256 M parameter, so that will be down. But otherwise, temporal plus physics, of course, I'm expecting it to be poor. Temp compass. See the difference between the RAM usage,
Yes.
phenomenal. So edge deployment is definitely a big uh, win for these small VLM series. But if you have compute, like I think there will be better options,
Yes.
like much better options. And if I see efficient OS, it fails miserably in chart QA, then text VQA.
Well, let's see the training data. Chart understanding has 12%.
No, this fails. Efficient OS fails quite
Mm-hmm.
poorly there. Mm, got it. Anyone has any other observations to suggest?
I just had a doubt. So, is the testing data and the training data similar? Like, have they trained on the testing data? Because the recent trend in papers have been that these small LLMs and VLMs are just fine tuning on that, and then they're pushing out the results.
OpenAI did it in some of their papers, like in the that one when they released the O3 or O1, like they trained that on that task of or they did RFL on that particular task and did it. Like, of course, it will be unethical if they train their models on the benchmark. They should not have done that. I don't think Hugging Face would do that. Hugging Face is one of the respected companies who hold the benchmarks quite sacredly. I cannot say that for Llama, but Hugging Face is still someone who feels that benchmarks should not be polluted. So I
Fair enough.
wouldn't, I wouldn't doubt that they trained on the benchmark. But having said that, I 100% believe that benchmarks are not a real test of how the models perform. Like we have seen very contrary results to benchmark. It's very determinist, or very determined by the kind of task that you are working on. Even if it is closely related to the benchmark, you cannot say that a model performing best on a particular related benchmark will work best for you.
Hmm, makes sense.
Right.
So next is how they deploy their small VLM on edge devices like phones.
Mhm.
This is just a visual thing that you can see. You can also download it, the app. I tried it, but it didn't work.
You tried it?
Yes, I tried downloading it, but I couldn't find it. Let me check. Okay. Ah, yes, it was not on the Play Store. Maybe it's on the App
Uh,
Store.
no, maybe.
Okay.
1 second. Can we go back? I'm just trying to see. Actually, if you look at it, you can find the milk in the refrigerator shelf near the bottom. That is cool. But the other part of it is like there's another aspect of it that the maybe someone is pouring in coffee from the machine or something.
Hmm.
So even with the cherry picked examples, like of course not the fault, they're playing with some models which are of course less capable of reasoning or understanding. But even in the cherry picked example, you can see that the reasoning is not, or the understanding is not spot on.
Hmm.
It's saying likely a coffee maker. Like, what else could it be? It's the coffee maker, of course.
Hmm.
There's no ambiguity left. Like some brown color thing is coming in, and teas are not done like that. So round base and a circular top. What is a circular top? The top of the appliance is illuminated by a bright yellow light. Anyways, yeah. But
Can
yeah,
only-
go ahead. Sorry.
yes, it can only see the visual things and cannot interpret what do they really
Yeah,
mean.
yeah, yeah. The understanding is definitely missing,
Hmm.
and it's understanding some parts of it, and it knows how to present it in some coherent sentence.
Hmm.
I'm pretty sure if he had asked, like, where is the Tabasco? I'm not sure it would have done it. Or how many milk containers do I have? Maybe it would have failed
Hmm.
in the second example. Hmm. Cool, cool. Yeah, we can move ahead.
So next is
And
the
sorry, we missed the graphs.
okay. Yes. So
So tokens per second, like such a huge improvement in tokens per second. And of course, very intuitive, like lower the size, more tokens you
what
can
the
emit
size?
because,
Hmm.
yeah, because more RAM is available, VRAM is available. But, 1,000 tokens per second with a batch size of 64, that is pretty impressive on 800. I don't remember like what was the benchmarking that we did. Let me try to find out. We also benchmarked the GPUs on 1 second. 1,000 throughput tokens per second. Actually, we did it for textual models, and hmm, actually we had 33,000 tokens per second in our experiment. Tokens per second, 33,000 with a batch size of uh, 8. So maybe it's a factor of vision language models. That
They
is
have a
And
separate.
ours was, I think, on a 800. So and these are running on.
sorry.
Ours was on different hardware, right?
No, it was also an 800.
800. Okay, these are on, I think, ProBooks.
No, the above graph,
Above one is of
Okay.
800.
Okay.
the top graph. So there they're saying 1,000 tokens per second. Our benchmarks on 800 running a textual LLM basically. It's the batch size of 8 is 33,000 tokens per second.
Maybe it's a thing with VLMs. They have to do a lot of processing with the image, and then the LLM part begins later.
Right. Possibly.
Mm-hmm. Yes, maybe that.
But 33 times lower. Like, okay, we can move.
So then we can move on to the conclusion. Um, so I saw some of the models that were fine-tuned on downstream tasks like small dockling and BioVQ and called SmolVLM. So one major theme among all of these downstream models was that they had structured prompts which you can give to a model. For example, you gave it an image, and there were a structured set of prompts. Ki, give me a OCR of this document, give me a OCR of this image, because they cannot interpret entirety of the text that you give. So I tried one of them, a small dockling, and it works pretty well. And next is focus on how small changes at each stage of the training could impact the performance of VLMs at compact stage. And yes, so
Cool. Cool. Thank you, everyone. Thank you, Ayush, for the detailed presentation. Would love to kind of understand from the new joiners, Girisha and like, how did you find it? What were your takeaways?
I totally loved it. I think it was very insightful, and especially the part where we were brainstorming about why increasing the video duration improves the model and helps it learn better. And since I'm still learning and exploring this field, I hope that I also get to be a part of future discussions where I can contribute more, because I found it very interesting and I love the way the results were presented, and I love the way it was a very good and insightful discussion overall. So I really enjoyed it.
Sure. It feels like a testimonial right now. You know, where you poke a camera in someone's face after they get a service done, and you're like forcing them to say something good about you. But of course,
No,
like that's not an intention here. You can
yeah,
even
definitely.
say that, okay, we missed any part of it. Like it's totally collaborative here. So you can even say that, okay, I would have loved to find XYZ better done. So we can collaboratively try to do it better next time.
Yeah, I hope as I learn more and more, I would be able to also like contribute to that side of the discussion, not just the positive one.
Sure, sure. Perfect. Uh, no, that is great to know, Pooja.
I've whatever I've learned from Pooja Didi. She's a huge inspiration at our university,
Wow.
not just for
Very,
machine learning, but for everything tech, like everything. Seriously.
very nice. Very
Mm.
nice. I love this kind of shout outs.
Yeah, because like
Oh,
I've worked with Garisha like really closely. So
hmm,
she's always that kind of a person where you tell her something, she'll make sure she does it and she completes it. So even here today, I'm sure that she is going to be one of the persons who's going to read the paper again and then come back with questions.
very
Yeah,
nice.
Yeah,
definitely.
that's something.
No, that is amazing. So, Girisha, you have our email. If you read the paper and want to discuss or brainstorm on anything, like, of
Okay.
course, feel free to shoot an email and we
Okay.
can get on a discussion.
That would be really good. Yeah.
Yeah, just adding to it, like we could have like initiate the community for this kind of use case. Like if we want to have discussions, we can have a
Right,
WhatsApp group or Discord, something like that, and start working
right,
on this.
right, right. Yeah, yeah, we can work on that.
Yeah. Thank you.
And how about you here?
So I'm going to give another testimonial. It was really great. Honestly, being a first year student, I thought that this session was going to be really heavy for me, but how it was explained, the discussions, they were really engaging. I learned a lot today. So moving on to the testimonial, it was great. What do I say more? Thank you so much for the session. And I completely agree with Girisha Didi. I would love to learn more and more about this topic and Jenny in general and be able to contribute more to the discussions.
Thank you so much here. First of all, a very unique name here. Honestly, I first thought someone from Japan is going to join us.
No, my name just means heart in Hindi, I guess.
Here, that's hard.
Yes.
Oh, nice, nice. But yeah, I'll not ask this kind of question next time, probably. It feels so much like that fake testimonial pose. But anyways, no, thank you so much for your warm comments. I'm glad you both had something to take away from this session. And, I'm glad others also had something to contribute, something to take away. And the next session, we'll soon release what's going to be the topic for the next session. It will be next to next week. Um, if no questions, we can all take 10 minutes back.
Sounds good. Thank you so much.
Cool. Thank you, everyone. Thank you again, Ayush. Thank you, everyone. See you again later.
Okay.
Bye.
Thank you.